This video will cover everything in Unit 4, which were all those chapters covering probability. Anna is a skee-ball player and she always rolls for the 50-point slot. She's collected enough data to make this probability distribution showing what's the likelihood of her scoring any given number of points. So we have that in this table here, and the first question is to find and interpret the mean number of points that Anna will score on a single roll. So to find the mean from a probability distribution, we're going to do x times p of x. X is what our variable is. So our variable is the score that she's going to get. Each of those variables has its own probability. So we just do the score times its probability, add them all up. We get a mean of 23.8 points. And since we're asked to interpret this, we want to write a statement something along the lines of, on average, Anna should expect to score 23.8 points for every roll of the ball. Next up, let's find the standard deviation. This one's a bit more complicated. It's x minus the mean squared times the probability. When we add those all up, that's going to give us the variance, which we'll need to square root. Both of these equations are on your equation sheet. So we have 10 minus that mean of 23.8. We square that value because we want to make sure it's a positive, and then multiply it by its probability. We do the same thing for each value in the chart here. Add those all up, we get 159.56. Since this is variance, this is in units squared, so this is really square points. To switch it to standard deviation, we're just going to take the square root of the variance, and we get 12.63. On average, the number of points Anna earns per roll will be 12.63 points away from the mean of 23.8. Remember, standard deviation is the average distance from the mean. Moving on to combining random variables. Let's say Anna rolls 9 balls in a game. What's the mean and standard deviation for the number of points she will earn across those 9 rolls? So the mean for a single roll was 23.8. Standard deviation was 12.63. Now we're talking about taking 9 rolls. The mean we find logically, just 9 times that 23.8. We would expect her to earn an average of 214.2 points. Standard deviation is not quite as average. We can't just add standard deviations. Instead, we're going to add the variances. So variance is the standard deviation squared, and we're doing that for all 9 rolls. Okay, I skipped the 6 in the middle there. Another way to write it is just 9 times that 12.63 squared. That gives us 1435. Square root that, we get a standard deviation of 37.89. So in a 9-ball game of skee ball, Anna will score an average of 214.2 points with a standard deviation of 37.89. Now that we know that information, what's the probability that Anna scores over 300 points in a 9-ball game of skee ball? So we just found these 2 parameter values, and we can put them into a normal model. So it is the mean of 214.2, standard deviation of 37.89. We want to find how unlikely is it, or how likely is it, to score 300 points or more. So we need a z-score. We get 2.26. It's above 2, so we know it's unusual. It should be a small probability. Now, you don't have to write this. A lot of you guys do. I'd recommend you don't. If you do write it, you need to write these labels. So you can't just write it with the numbers filled in. You have to write what each of those numbers is representing. Okay, that's going to give us 1.19, which is our answer. Assume each roll is independent of the next. If Anna rolls 9 balls, what's the probability that exactly 2 out of the 9 are 30-point rolls? This is everyone's favorite type of probability problem, the binomial probability. We know it's binomial because it meets all 4 criteria of bins. We have a binary set of outcomes. Either she makes that 30-point roll or she doesn't. Trials are independent. We have a fixed number of trials since she's only rolling 9 balls, and that success probability is constant at 19%. So we're going to plug everything in here. 9 choose 2. We want exactly 2 here of those 9 to be 30-point rolls. 0.19 squared, 0.81 to the remaining 7 trials. That gives us 0.2973, which is our answer. If you look in your distributions menu, which is where you find normal CDF, TCDF, etc., you're going to see functions for binomials. There's a binomial PDF, which we use when we just want to find the probability of one thing occurring. That's what we're doing here. We would use CDF if we were combining multiple events, like the probability of 2 through 5. So again, if you write calculator notation, which I prefer you didn't, but it is acceptable, provided you label all of these individual components. In this problem, we're going to change the wording from exactly 2 out of 9 to at least 2 out of 9. So when we think about at least 2 out of 9, that would include 2, 3, 4, 5, etc., up to 9. That's a lot of things to add together. Rather than do it that way, we can just subtract the complement, and the complement of 2 through 9 is everything that's not included in that range, which is 0 and 1. So let's find the probability of that occurring and subtract it from 1 to get the probability of 2 through 9. So the probability of getting 0 would be this. Probability of 1 would be this. Add them up, we get 0.4670, and we have to do 1 minus that to get our answer, 0.5330. Binomial CDF is the option here, the calculator option. On the 89, you can just put in a low of 2 and a high of 9. On the 84, you have to put in 1 here. Okay, it's always going to find the area underneath it. So we can't do this. Right? We can do this and subtract it from 1. So 1 minus that calculator notation with everything labeled. If Anna completes a 9-ball game of skee ball, what's the probability that the first 30-point roll comes on the 4th ball? Now this wording right here is actually irrelevant. We don't care about the whole 9-ball game. We only care about the first 4 balls. And what we need to happen is we need balls 1 through 3 to be something other than 30 points, not 30 points. Then we get to the 4th ball, and we want that ball to be the first one that results in that 30-point score. So to get not 30 points, we want anything that's not in that 19%. That leaves 81% for each of those first 3 balls. Then we get to the 4th ball. We want that to be the 30-point score, so 19% for that 4th ball. Multiply them all up, 0.1010. There are geometric probability functions. Geometric are for waiting time problems. We're waiting until the 4th ball to see this 30-point score. 4 trials, 19% probability of success. Part H, we're back to rolling a single ball. Given that she did not score 10 points, what's the probability that she scored 50 points? So it's telling us she did not score 10 points. We can take that out of the distribution, and we're looking only at 20 through 50. This is a conditional probability. It's on your equation sheet. This is the actual equation, but it's easier just to deal with this problem logically. What's the probability that after we take out this option, that she ends up with 50 points? So there's a 7% chance that she rolls a 50, but it's not out of 100% anymore. It's only out of the sum of all these probabilities, which is 68%. Simplify that fraction, 10.29% chance that she rolls 50 points if she hasn't rolled a 10-point roll. And lastly, a player receives 1 ticket from the game for every 10 points scored. What are the mean and standard deviation for the number of tickets won on a single roll? And it asks us to make a graph of the distribution for the number of tickets. Describe the shape. All right, so the mean, it had been 23.8. All of these values here are going to get divided by 10. So every 10 points gives you 1 ticket. So it's just like we take each of these, we divide it by 10, or thought of another way, we multiply by 1/10. Okay, we're scaling our data by 1/10. Remember back from Unit 1, if we multiply a distribution by a number, it changes measures of center and measures of spread. Compare that to adding a number to a distribution, it only changes measures of center and location. Okay, not measures of spread. So our new mean is 2.38. Our standard deviation also gets multiplied by that 0.1. We end up with a standard deviation of 1.263. Okay, it's asking us to make a graph of this distribution. All of these over 10 would just be 1, 2, 3, 4, 5. Okay, so anytime you make a graph, start off with a scale. Let's see, our biggest probability is about 32%. So I'm going to mark this up in thirds. So let's say this is probability 30, 20, 10. Okay, and I want to scale this out to make sure all my spaces are fairly even. So 1, 2, 3, 4, 5 tickets. Okay, and now we're just going to draw our histogram. So this is going up to 32%. That's a horrible rectangle, but I am drawing on a computer screen right now. 27% is about here, 19%, 15%, 7%. Okay, you want to make sure that your axes are labeled. We want to make our graph as neat and clean as possible. Put a title on the top, space out everything evenly, and describe the shape. We can see this is skewed to the right, and we found that center and spread, so I'm going to include that as well.